All right, welcome back. Today, we're on a mission, a high-stakes engineering mission. We are not just building another little feature. Nope, we're building a fortress. We're going to design the ultimate defense for our system, and it all starts right now. So if you remember from day 16, we built an absolute beast, a massively scalable cache using consistent hashing. It's super fast, it's efficient, but let's be totally honest with ourselves. Right now, it's a sitting duck. A single bad actor, one runaway bot, could bring that entire beautiful system crashing to the ground.
So, today we fix that. The mission is simple. It's critical. We build the firewall. We're going to protect our API and make our system truly resilient.
Okay, before we start letting down architecture, we have to understand the enemy. Why is our amazing API so vulnerable in the first place? Let's break down the actual threats.
It really comes down to three huge threats. First, the big one, denial of service attacks, or DDoS, where someone just floods us with requests. You can just imagine a storm of these spiky red orbs hammering our happy little green servers until they just flicker out and die. Second, API costs. If you're paying for a third-party service, every single unneeded call is costing you real money. And finally, just plain old resource starvation. A buggy script or maybe an overeager user can accidentally hog all the resources, starving out legitimate traffic and just completely overloading our servers.
Okay, so we know we need a defense. The next big question, the critical architectural decision, is where do we build it? Do we put it on the client side, in the server code itself, or maybe somewhere in between? This choice has some major implications. Let's look at the trade-offs, right? On one hand, we could build it directly into our application code, right on the servers. The big win there is total control. You can perfectly tailor the algorithm to your specific business logic. But it can get messy, and it's often tied to just one programming language or framework. On the other hand, we can put it way out front in something called an API gateway. This gives us centralized logic, it's way faster to deploy and manage, and it acts as this universal first line of defense for every service behind.
For our purposes, the choice is pretty clear. The API gateway is the most strategic place to build our wall. Seriously, think of it like a bouncer at the front door of a nightclub. It checks every single request before it gets anywhere close to our expensive, precious API servers. But here's the plot twist. A wall is completely useless without a smart gatekeeper. We can't just block everybody. We need an intelligent algorithm that can decide who gets in and who gets turned away.
So, what's the logic here? How does our digital bouncer make these split-second decisions at a massive scale? Well, the answer is this really elegant and powerful concept that companies like Amazon and Stripe use all the time.
It's called the token bucket algorithm, and the idea is surprisingly simple. Just imagine a bucket, okay? It has a fixed size. Then you have this other process, a refiller, that is constantly dripping new tokens into this bucket at a steady, predictable rate. Say, 2 tokens every second. Now, if the bucket is already full, any extra tokens just overflow. They're lost. So here's how it works in practice. Every single incoming API request needs to pay 1 token to get through the gate. When a request shows up, the system just peeks into the bucket. Is there a token? Great. It takes a token, consumes it, and forwards the request on to our API servers. So what happens when a huge burst of requests comes in and just drains the bucket? The very next request arrives, looks for a token, and finds nothing. The result is simple. No token, no entry. The request is immediately rejected, dropped right on the floor. And that is exactly how we handle those crazy traffic spikes and prevent our servers from getting overloaded.
Okay, so the algorithm is smart. It's elegant. I love it. But it has one huge requirement. It has to be incredibly, mind-bogglingly fast to work at internet scale. We are talking millions of requests per second.
And here is the reality check. We need a place to store all these token counts for every single user, every IP address, every API key. If we try to use a traditional disk-based database for this, we're done. We're toast. The latency of just reading from a disk is way, way too high. The whole system would collapse under its own weight.
The solution is an in-memory data store, and the king here is Redis. So why is Redis fast? It's actually really simple. It operates entirely in RAM. Accessing a disk might take milliseconds, but accessing RAM takes microseconds. We're talking literally thousands of times faster. This gives us the real-time speed we absolutely need to check and update millions of counters without even breaking a sweat.
Now, the real magic behind all this speed comes down to a single tiny command, incur, which is short for increment. It's an atomic operation, which is a fancy way of saying it's guaranteed to happen as one single unbreakable step. And that is critical, because it prevents two requests from tripping over each other trying to update the same counter at the same time. This one little command is the powerhouse that lets us handle millions of requests safely and instantly.
All right, we have the location, the API gateway. We have the brain, our token bucket algorithm. And we have the muscle, our lightning-fast Redis cache. It's time. Let's put all the pieces together and finally deploy our digital bouncer.
Let's just watch this thing in action. Here come the normal users. See them? Glowing green orbs just flowing smoothly through our neon API gateway. But wait, look over there. Here comes a spiky red orb, a malicious user, firing a torrent of thousands of requests. Our gateway instantly throws up a neon red shield. The response code flashes HTTP 429, too many requests. And just like that, the malicious red requests, they vaporize into dust, while the legitimate green traffic just keeps flowing, completely unaffected. Ah, that is beautiful.
But a really well-designed system isn't just a brute force wall, right? It's also a good citizen. We don't just block people cold, we politely inform them of the rules of the road. So when we send back that 429 error, we also include these super helpful HTTP headers. X rate limit tells the client the maximum calls they can make. Remaining tells them how many they have left. And my favorite, retry after, tells them exactly when, down to the second, they can try again.
And there you have it, a robust, a scalable, and an intelligent rate limiter. Your API is now bulletproof. But our job, as engineers, is never truly done, is it? We've protected our servers from the outside, but now we need to monitor them from the inside. How do we track which servers are dead and which ones are alive? Well, tomorrow, for day 18, we're going to tackle that exact problem by building a heartbeat mechanism. I'll see you there.